Hello, my name is Sampon Saichai. Today I will talk about my recent research done with Professor Gucci. The title is called Interpretable Intersection Control by Reinforcement Learning Agent with Linear Function Approximator. This poster is created based on our recent article published at IET Intelligent Transport Systems. The link to the full paper is given on the right-hand side here, so please check for more details. This work explores and investigates novel traffic signal controller we call agent controller. It is completely different from existing conventional traffic signal controller where timing parameters exist, timing parameters being commonly green signal duration, or it could be in the combination of green split and cycle length. So this mentioned timing parameters do not exist at all in so-called agent controller. So the way to develop agent controller or to formulate it is to use reinforcement learning, which is a machine learning paradigm to solve control problems or decision-making problems. Technically, the brain of this agent is called function approximator, abbreviated as FA here. So this FA takes state and reward as the input, and it outputs in return action that will control or interferes with the processes happening in the environment. And the essence of this research work is that in previous works, uninterpretable artificial neural network ANN has been used as the FA for the agent controller. So on the contrary, in this study, we try to investigate rather simple interpretable linear function approximator here. Next, for the methodology, as explained earlier, of course, there would be different learning methods based on the different function approximator. So first, batch gradient descent is used as the representative learning method, which is necessary for learning with NNFA. On the other hand, since linear FA is investigated here, we can apply actually another learning method. This is called least square temporal difference learning method, LSTDQ, abbreviated as LSTDQ. So this would be the proposed technique as I will show in the results section. And as I have mentioned earlier, we need to define the environment. So for this particular study, this is formally known as Markov decision process. The control environment is defined as follows. State features is consisting of information of the currently active signal, and this is appended with len Q length. Reward is the negative sum of Q lengths. Why it is negative? This is because the formulation of RL is for maximization of sum of rewards. So maximization of sum of negative Q lengths will result in minimization of Q lengths. As for the action, this is formulated as a selection of traffic stage. I will show later in number 3 what are the traffic stages here. So for this particular study, simulation-based study, rather simplified, simple intersection setup is made. So it is just an isolated intersection with uncomplicated structure. Each lane is a dedicated lane, not shared lane, and you can see the boundary conditions for sensing here on the left. So these are the allowable traffic stages to be selected by the agents, and each of these is conflict-free. So at any time, the agent can select any of these 8 allowable traffic stages. And for this particular setup, we are focusing on a rather short decision interval of 1 second. So every second it can think again what to select, what to choose next as the next traffic stage. And there are 3 arrival patterns here. Moving to results and discussions, I have compared 3 major settings of function approximator FA and learning method. So the first combination is in FA with batch gradient descent BGD. Second is linear FA with batch gradient descent, and the third is linear function approximator with LSTDQ, the least square method. Please pay attention to these 3 learning plots. So the most right-hand side here represents the state-of-the-art method that has been found in this study. So linear FA with LCDQ. The major difference among these plots are in the horizontal axis, where you can see that the scale is totally different. We see the convergence that can be attained around 10 or 20 iterations, whereas in the first 2 settings, it would be very lengthy thousands of iterations, or at least 1,000 of iterations in the second case. So this much faster convergence could be achieved by the nature of the least square learning method. It is leveraging the convexity of the loss function, which is a property of this linear formulation, and we can achieve much better learning data efficiency and therefore learning speed. And here we can demonstrate the effectiveness of the linear agent controller. And when it is compared with the more conventional traffic signal controllers, I have put here in the comparison the pre-time controller and passage time actuated controller, we can see a significant improvement in terms of average delay and average number of hops with these tools. So although the moderate higher intensity level, we can see that the performance is rather competitive with the passage time actuated controller. However, if we further reduce the arrival intensity, we see much more and more competitive advantage of the R agent controller. So this sums up as my research. Thank you very much for your attention.